We see robots being used for more and more aspects of our lives, many of which most of us don't even know about. Before you order a product, this is stored in a warehouse along with many others, but when you press that simple button, a very complicated process starts happening, from taking the correct product to sending it to your house. All aspects of that process have started getting automated. Robots navigate around the warehouse, locate the product and bring it where it needs to be. Other robots transfer and process the product until it gets to the delivery phase. Then also some companies test robots that take them and bring them to your house. But have you ever wondered, how do those robots do that, when they experience so many different, unknown environments? How do they know where they are? Well, this is where SLAM, or Simultaneous Localization and Mapping, comes in handy. To understand what SLAM does, think about what you're doing when you enter an unknown building. You observe distinctive characteristics of it, which when you see remind you of where you are relative to the previous time you saw them. Also, by wandering around the building, you create in your mind a map that describes the relation of all those characteristics positions with each other. Robots do exactly that, and they do it using data from two sources, sensors and odometry. A sensor is usually a LiDAR, sending laser beams 360 degrees around it and measuring distances, or a camera, possibly depth camera. Using the sensors, they mark certain characteristics as landmarks, or compute the probability that each position is occupied. Either way, that's the map of the environment. Odometry data are those acquired from usually motor encoders, thus the velocity of each wheel at this time, and provide a crude estimation of the robot's position. What we want to find is a state, with the robot's position and orientation and a map. In order to do that, we store for each possible state the probability that is the current one. Bayes' rule is what allows us to update the desired probabilities after acquiring new data. SLAM uses Kalman filter, which is an application of the Bayes' rule that uses odometry and sensor data to improve that belief, in two steps. The prediction step uses the odometry data to estimate the new state, while the measurement update step uses the sensor values to improve the accuracy of that estimation. This exciting concept was a perfect opportunity for me to build a robot on, to make it locate itself, map and navigate around my room. To do that, I used the Robot Operating System, or ROS, which contains useful libraries for that purpose. This idea, some of the chassis features and electronics were inspired by James Bruton's ROS robot, so you can check it out as well. Let's get into building. Starting with the hardware, the parts that I needed were two motors, two motor drivers, two encoders, an Arduino to control those, and the Jetson Nano as the main board. To power them, I used the 12-volt LiPo battery for the motors, a step-down module for the encoders, and the power bank for the Jetson Nano. After ordering the parts, I got right into designing the chassis in Fusion. I designed the motor and encoder mounts, wheels, gears, the respective lower-level platforms, and the higher platform for the electronics. Then I 3D printed most parts using my Ender 3 and connected them using some metal parts, like a couple of aluminum extrusions, a rod, some screws, and two bolt casters for stabilization. I put on and wired all the electronics, which required some soldering as well, and was ready to move on to the software. The first part was using the Arduino to control the motors and measure the encoder speeds. The motors are controlled using the motor drivers, to which the Arduino sends PWM, or pulse width modulation signals that simulate analog signals in a digital device. The drivers then provide the necessary voltage to the motors to change their speed. Encoders have two pins, A and B, that give a high or low signal based on the encoder disc gap positions, with a phase difference of 90 degrees. To measure their speed, we detect the change of phase signal from low to high, which one pulse, and check B's value to determine the direction. We need to convert the pulses per millisecond to meters per second, so I put a measuring tape and made the robot drive 1 meter, and noted the encoder counts. However, that doesn't give us the ability to accurately control the wheel speeds in meters per second. Yet. To do that, we use a PID, or Proportional Integral Derivative Controller, which takes the encoder speeds as an input and changes the motor voltage as an output, to achieve a desired speed. After some fine-tuning of the PID parameters, it was working almost perfectly. One more conversion is needed though, as ROS provides the velocities in terms of their linear and angular components, but with a simple formula we can compute the wheel speeds from that. Now we can use the Arduino to control the robot speed, but we needed to be able to receive velocity commands from ROS and send the wheel speeds to it. This is done using the Jetson Nano, which communicates with the Arduino using serial and the serial transfer library via USB and forwards the required data to and from ROS. Two-way communication via serial isn't so trivial, so after some trial and error, I ended up with a handshake in the beginning, with a message from the Jetson Nano and a response from the Arduino, and then in each cycle of the loop, they first send and then receive the required data, or vice versa. This synchronizes the cycles in both boards. However, we need some more math to get the data to the desired format. While currently we have left and right wheel speeds, for SLAM we need to convert those to their linear and angular velocity components, but also time integrate them to estimate the position of the robot. This is done using some more formulas, and when tested it gives some pretty good results. I implemented all that previous functionality from scratch in a dedicated ROS node using Python. It's now time to get into mapping the room using the encoder data and of course the LiDAR, which runs using its own ROS node from the RP LiDAR ROS package. Before being able to make a map, we need to configure the robot's components position relative to each other, especially the LiDAR's position, which is done using a URDF file and the default robot and joint state publishers. Then we use a SLAM toolbox package that takes all that data and creates a map of the room using SLAM, and it works pretty well. But as a bonus, I also want to make the robot autonomously navigate to certain places. So I used Nav2 buckets to be able to do exactly that. It takes the computed map from before, a planner node computes the optimal path to that goal, and the controller node sends velocity commands to follow that path. Here's the robot in action. This is the current state of the project, but what can I do with it? The ultimate goal is making it perform useful tasks. So for that purpose I will add the camera to it and use the enhanced AI capabilities of the Jetson Nano to, for example, detect objects. Next I will probably add an end effector, like a grip or a robotic arm, to interact with the environment. So this is it for now. You can find the GitHub repo with the code for the project, an article describing the building process in depth, and the links to the used libraries and James Breton's video in the description down below.